with these reactions, again, we're building on something for a reason, and we'll start to see that on Wednesday when we actually when we start to bring synthesis into this whole thing. Okay, so if you'll remember back, we can take an alkyne and we can hit that alkyne with hydrogen and palladium or platinum or ruthenium or nickel, and we can reduce that all the way down to the alkane. And you have to ask yourself the question: is that synthetically useful? Well, at least we can do it if we need to. Okay, we can get rid of the alkyne all the way to the alkane. We can also take hydrogen over the Lindlar catalyst, right, which is going to be that quinine with lead acetate and palladium carbonate acetate, and we deaden it, right? We poison it so we make it not as reactive. And in doing so, we came up with a really, well, that's not going to work because it's not. Let's make these methyls. That'll actually work. Make these methyls. Sorry about that. Okay. So with that, we saw that we could take this less reactive form and form exclusively the Z or the cis form of the alkene. Again, this will play into chapter 15. Okay, we'll see this because we're going to learn how to make these compounds with alkynes. Really cool chemistry. In the free radical chapter, we see that if we use sodium in ammonia at about 30 or minus 30 degrees, basically liquid nitrogen, minus 30 degrees, and really cold, we actually can form the E, the Einwagen, okay, or the trans, okay? Einwagen and Zuthwagen are E and Z. So we can form the trans exclusively. So we can see synthetically, the alkyne is going to have quite a lot of useful tools to it, because we're going to get into stereochemistry when we get into, again, reacting this with with like an epoxide or with osmium tetroxide, and we're going to see handedness here with these molecules. So the question is then, what's going on here? And the reason why these reactions aren't put together is because this is a free radical reaction. All right, so what's going on with the free radical reaction? When I take sodium metal and I solvate sodium metal in ammonia, liquid ammonia, cool it down, what happens is a delocalization of this electron. Now remember, go back to general chemistry. Sodium has electron configuration of sodium. Sodium would like the electron configuration of neon because we're full. The N equals 2 energy level, the principal quantum N equals 2 is full. That's why it's very easy for sodium to lose an electron. Okay, cesium, if you remember from our little video, wants to lose an electron the most. It's the most reactive. Okay, that electron comes off most exothermically. Sodium and potassium are somewhere in between. All right, so sodium specifically, it's been figured out, which is pretty cool, what we call solvates the electron. And the way we actually abbreviate this, we put this ammonia, okay, and it solvates that electron. It solvates the electron. And I've done it, I think I've already told you, I've done this reaction. It's actually really cool. It's really an opaque blue, kind of like a glacier blue. Really, really pretty reaction, all right? When that happens, and you throw in an alkyne, okay, throw in the alkyne, this electron forms with that electron, and that electron goes there. Now that's bizarre, to be honest with you, because it makes a really high energy compound, and if you think about this, you have a real high energy compound, but you're at minus 30 degrees. So it's one of those just kind of like, huh? How is that actually happening? And the answer, of course, is going to be, remember these sp electrons out here are available for attack, right? They're out there in those outer lobes, and they're pretty easy to attack those. So when this process happens, it looks like this. Okay, so it puts a full negative charge there because it has its electrons, and it puts a radical on that. Isn't that weird? And you have to ask yourself, okay, that is just a kind of a weird reaction. Because then what happens, this whole process is done in some kind of an alcohol, typically methyl alcohol or ethyl alcohol. So you can see that if it's done in alcohol, then over here, okay, then this pair of electrons grabs that proton and makes the anion, okay? So it goes to this. And it's at this stage of the game that your actually not quite yet. Once that happens, I'm gonna go ahead and erase a little more over here. So when that happens, again, you have electrons, free electrons being solvated in the ammonia. So this then picks up another electron, forming another one of these carbanions. It's this carbanion now that forms our ability to cause this thing to go trans, okay? You can see that. It wants to put the big methyl groups farthest away from one another, right? So when this picks up another solvent proton, you can see that that lone pair grabs that, and it goes to product. Okay. So the overall reaction is a free radical lone pair, electron lone pair reaction. And you can see, again, here is where we put our largest groups opposite sides of the alkene, because they're more bulky than a lone pair of electrons. Okay? And then when that does pick up that proton, it puts that proton on, and you just made a trans, or an E, Einwagen alkene. Okay? It's pretty cool. So if I have an alkyne in my synthesis scheme, I can reduce that selectively all the way to the alkane. I can reduce it selectively to the cis, or I can reduce it selectively to the trans. And that's actually really synthetically a very useful, and whoever, again, I don't know the history of how this one was figured out, but that is a really cool reaction, okay? Kind of a unique reaction, but really, nonetheless, really cool. Okay, any questions on that? Okay. Okay, so our next one is fascinating in that it is a very complex reaction that does a very minor thing. So we have this compound called AIBN. Here's the thing. When you see the initials AIBN, think free radical. Okay? This generates free radicals. So this is azo-bis isopropyl dinitrile. Okay? It looks like this. It's azo bis isobutyl nitrile. Okay. This is an azo functional group right here. Azo is an N double bonded to an N. That's called an azo. So it's azo, bis, isobutyl, nitrile. Okay, CN is a nitrile. So that's where the AIBN comes from, that's its name. And so this molecule here, under heat, when you heat this thing up, what happens is actually pretty interesting. This and this form nitrogen gas, so it bubbles off nitrogen gas, but it forms this free radical, again, free radical chemistry. All right? So you actually get out two of these. Okay, plus nitrogen gas bubbles off as a byproduct. Right? Now, if you put that in the presence, because this reaction is typically done in the presence of kind of a weird tributyl tin hydride. Okay. This compound, oops, let me do blue for the mechanism. These two typically work together. Okay, and it puts that free radical on there. All right. And ultimately what happens is the tributyl tin and then goes in and attacks it goes in and basically attacks this compound here. Okay, so it puts the bromine on here. And ultimately what happens is that electron there on the carbon picks up a hydrogen, actually basically picks up the hydrogen off this carbon here. And you go to, so here's why I say this in kind of like one of those, that's a lot of reaction to go from an alkyl halide to an alkane. Okay. But if there's a free radical reaction, that is important if you do need to do that step. So it kind of looks like this. So it's a way of removing a halogen from from an alkyl halide. Okay. So AIBN is typically, you think of it when you see that, even when I'm teaching advanced organic chemistry, you think of free radical chemistry. That's what AIBN is because of this azo compound that forms nitrogen. Okay, so here you have it. It's a lot of reaction to do that. It's a lot of work, right? Just remove a bromine. So, all I'm saying is I'm not sure how practical, yes?
Sorry to backtrack.
You're good.
Why is the nitrogen, wouldn't it be charged in the beginning when it's azo?
Nope.
No?
Remember, it has its free electrons on it. It has its lone pairs here.
Okay.
Yep, it's happy.
Okay.
It's happy. It likes 3 bonds. Yeah. And it still has its 3 bond. You know, when it becomes nitrogen, it gets that triple bond, and it still has its lone pairs out there. It's happy.
Okay.
It's a happy little guy. In fact, that's one of the strongest bonds next to the carbon-oxygen bond that we have. Very, very inert. Carbon monoxide and nitrogen are the 2 strongest bonds. Okay? Now, this one is more practical than this one. I'll just say that. This is a classic free radical. AIBN is a classical free radical reaction. This one is actually really practical. So I think between the sodium ammonia going to trans versus the Linlar going to cis, those are very practical reactions. I would probably translate, when I say practical, know those. Will I ask you that? Maybe not. Will we use that? Possibly. So that's one of those reactions. I look at that and I say, when would I want to do that? Because what am I ultimately doing with this reaction? Well, what I'm ultimately doing with this reaction is I'm taking the handle off. And this whole class is putting handles on. So maybe I put the handle on, do chemistry, and then need to take the handle off. That's where you might use this, okay? But for the most part, I'm just basically killing what I really need. And now I've got really got a dead molecule, okay? So practically, where would you use that? In all the years I've ever done chemistry, I've never done that reaction. I've never even seen that reaction done in a working laboratory. So it is what it is. Now this one, on the other hand, is really important. Let's go back and let's review first semester. If I take 1-butene or but-1-ene, and I hit this with HBr, and I do what we would term an addition reaction, if you remember back. Okay, so this is an addition reaction. In the process of doing this reaction, if you remember, this grabs this, kicking that to there. Okay, this is Dr. Bell spent quite a bit of time on this. That sets up the possibility to have 2 different carbocations. You might have learned them as carbocations. Okay? I have 2 possibilities for that carbocation. My electrons here can either go this way, leaving a carbocation there, or they can go this way and leave the carbocation there. Okay? So I have 2 choices. This one, through the process of hyperconjugation from the carbons, can resonate into or lower the energy barrier of this carbocation relative to only one carbon being able to put its hyperconjugation into that carbocation. So that's why we said a primary is not as stable as a secondary carbocation. Therefore, when my nucleophile comes back in and it attacks the carbocation, or it attacks the carbocation, I have 2 choices. I have this and this, okay? This is going to be my Markovnikov, my Marky Marks major, and this is going to be my non-Markovnikov or my minor, okay? That's review. That's what you had last semester. It should be somewhat, at some level, that should be up there in the ether. Now, here's what's really cool, and this becomes very practical. This is your major product, and we're talking major by a long ways. And I don't know, do you guys remember the ratio that he gave you on this particular one?
Could have been like 98 to 2.
Yeah, it is. It's above 95. Okay, so here's the thing, and I'm going to say greater than 95%, less than 5%. Okay, that would be, and that's an ish. I'm going to put that in an ish. It depends on the system. All right. what ratio you're gonna get there, but by far that. No, so here's the thing. What if my synthetic scheme, I really need the anti-Markovnikov. I'm not gonna be able to really practically do a fractional distillation for 5%. Okay, that's a lot of work. Is there a way that I can maximize the non-Markovnikov if my synthetic scheme required it? Okay? And the answer is, well, yeah, of course there is, right? There's always someone that's figured this out. So here's how this works. If I put my HBr in with hydrogen peroxide, I only get out one product. Huh. Well, that's pretty cool. What's going on? Great question. So here's what's going on. Since we're in the free radical chapter, it's probably going to be a free radical mechanism, right? So let's take a look at it, because this is an important one. Is this one important? Sure. I'm not going to put that in the important category. It's a class, it's a historic one. AIBN is a classic free radical, but like I said, it's not a very practical reaction in the real world. Okay, this one happens to be really practical, because there are times where I do want the non-Markovnikov. So what's going on with this molecule? Well, so what's happening with this molecule is when I have my peroxide and I heat the peroxide up, but this doesn't take photochemistry, this is just thermal. This thing's gonna break open. It breaks open basically to a free radical, so 2 of these. Okay, free radicals. So here's what you want to be thinking. Once I have a free radical in this reaction, then what happens is this molecule, or this entity, this radical entity, sees another pair of electrons and says, okay, well, I can react with that. I'm reacting, I'm high energy, I see vulnerable electrons, I'm gonna go attack them. Okay? So with that, this electron and this electron get together, but here's the thing. Notice, I can put blue here, or I can put red here. Okay, so watch this. I have 2 possibilities. I have blue oh crap, sorry. Anyway, probably should put HBr in there. Hang on, sorry about that. I'm like, well, we kind of are doing the bromination thing. So that then sees, it's the bromine that actually does it. So the HBr comes in, and it's the HBr, it's the bromine, not the hydroxide, sorry about that. Okay, so it's the bromine now. When it looks at the alkene, okay, the blue or the red, okay? So watch what happens. One possibility is this. The other possibility is this. Okay? So let that sink in. Because just like we had our addition reaction over here, we're looking at energetics. So let that sink in, let you get that drawn, and let's talk about it. Okay, so, about done? Okay. So think of this. We know that in carbocations, tertiary are better than secondary, which are better than primary, which are better than methyl. Right? They're more stable. Why are they better? Well, they're lower in energy. So when you look at an energy scheme, what you see is a lowering of the energy, right? Lower energy. So as we go up, so secondary, okay, and then primary, you're lowering this energy, and you're lowering the energy, making it more stable, because this has, again, more hyperconjugation that can come in and stabilize that carbocation. Because if you remember, the carbocation itself is a trigonal planar bipyramidal, right? Or trigonal bipyramidal with its lobes coming out. So you've got a lobe coming out at you, and you've got a lobe going away from you. So it's a trigonal bipyramidal intermediate. And it's basically the nature, when you look at this carbon, and you see that its electron is out here, it's this overlap of this carbon that actually contributes to helping stable, so the story goes, okay? So that's why we know that secondary is more stable than primary, which is why we get this distribution. What's going on over here? Well, let me ask you this. Which of those radicals is more stable, blue or red?
Blue.
And why?
Because it's got more of the
You got it.
from the carbons.
This, just like over there, this is a trigonal bipyramidal with an electron. So, if carbocations are stabilized through hyperconjugations, radicals are also stabilized through hyperconjugation. That makes this lower in energy than this. Okay? So when this one now comes in and finds its other electron, which is going to be from water, because remember, you did form water right here. So it grabs this electron, reforming this, so it's a propagation step, but in turn, you get this as the only product out. Okay? And that tells me that the secondary radical is way more stable than the primary radical, because I don't see any of the Markovnikov product, even though with the addition I do see a tiny bit of the non-Markovnikov. Okay? So that free radical carbon intermediate secondary is far more stable than the primary. Okay? 3 reactions. Sodium ammonia, AIBN with tributyl tin, and non-Markovnikov free radical bromination. Okay, so let's put this together and we'll see what we're kind of, because that's it. We're done with chapter 12. There's some other reactions in there that I'm not going to hold you accountable for because that we just don't. There's some that we will never use, and it's almost like, well, let's just add a few more reactions to add a few more reactions. I gave you the ones that are practical that you will actually see someday, might see someday, and should know. Even the IBM one, I'm a little hesitant on how much I would push to have you memorize that one, but I think it'd be good to have it in your toolbox. Okay, so let's say a couple things here. Let's use, and we'll have this on what's the day? Friday, Wednesday. So let's say we had a molecule that looked like this. All right? And I wanted you to synthesize this. And these are where we're going to begin to build on our synthetic scheme. So starting with an alkyne, can you form an amine? Here's what I want to begin to do. I want to begin to look at this molecule and ask myself, in my toolbox, what reactions do I remember form amines? That's where I want to go with this. And up to this point, since we haven't had the chapter on amines, it must have been last chapter where I began to build on the idea of oxidation reduction. Oh, so I know that amines can come from two different things. Anybody remember what they are? Azos and nitriles. So nitriles and azos, okay? Those are the two things that those are the only two things in my working toolbox right now that I know amines come from. That's it. Because again, we haven't even had the chapter on amines. The only time I've really talked about amines up to this point. So that tells me I've probably reduced one of these to the amine. But here's what I want to begin to ask. Which one and how would I know? Well, if I have the N3 on there, okay, the N3 just gives me the amine. The nitrile adds a carbon. So here I want to look at how many carbons do I have? I have 1, 2, 3, 4, 5, 6. Here I have 1, 2, 3, 4, 5. So that tells me I added a carbon to the end of this molecule. I went from 5 to 6. So that tells me that this probably came from this molecule. Okay? 6. That probably came from that molecule, right? But on this molecule, my handle's out over here. So I need to somehow make that carbon want to attack to put a nitrile on there, because it's right there. So this is my new bond. That's my new bond. So I have to be asking myself the question, do I know a reaction that puts the nitrile on? Oh, I do. If I go back to my nucleophilic SN2 substitution reactions, I know that that would have come from that. Nucleophilic substitution. This is a great nucleophile. SN2 says that I would do that. Okay? And you have a whole list of good nucleophiles coming out of that chapter. Right? Well, do I know how to form this thing? Well, this is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. So somehow I had to put a bromine there. How can I put a bromine on the end of a molecule? Oh, I know bromines can add anti-Markovnikov to terminal alkenes. And I know alkenes can come from alkynes. Okay? So, building it forward, what would this look like? Well, my synthesis would be something like this. I take my alkyne, my 5-carbon alkyne, and I reduce it. Now let me ask you a question. Why did I pick hydrogen and Lindlar? I had 3 choices there.
Because the Lindlar catalyst won't completely get rid of your double bond.
Boom. And why didn't I use sodium and ammonia? Could I have used sodium and ammonia?
Yeah.
Yeah. Why do you think I did? Probably you don't really know or care, but sodium ammonia is actually a very difficult reaction to do. Lindlar, you throw it in there, bubble a little hydrogen, done. Okay, it's a really simple reaction to do. Always go with the most simple. Setting up the sodium ammonia takes half a day, and it's just a really difficult reaction to do. So this one takes 30 minutes. So I'm gonna do that. But I'm not gonna use hydrogen and palladium. Why? And that's what you were
Because
saying.
that will completely
That will
reduce.
completely kill it to the alkane. I want to keep the handle on my molecule. Okay? Now, I have 2 choices. I can put now I know I can put a bromine here, or I can put a bromine here. Which one do I prefer? Well, I kind of need it out there on the end, so which one am I gonna do? HBr and peroxide, that causes it to go exclusively to the anti-Markovnikov. Okay? Okay, good? Tracking so far? Good. Now I'm gonna do my SN2. I'm gonna hit this with sodium cyanide. Really nice reaction, beautiful reaction, probably over 90% yield on that thing. That's gonna put my nitrile on out of the end. That adds that 6th carbon that I really looked for, that I really wanted. Okay? And then now, I'm just gonna beat it up with hydrogen and palladium and take it all the way down to the amine. Okay? Okay, so yes?
Can you explain like what Emma and you were talking about, like what happens?
Yes, so if I take, good, if I take this and I hit it with hydrogen and palladium, okay, I'm gonna get this out. Okay? Hydrogen palladium is too powerful. It's gonna go from the alkyne all the way down to the alkane.
Okay.
Okay, I've just lost my handle on the molecule.
Oh.
And to put a handle back on this, whew, I'm gonna put a bromine, bromine, bromine. I'm gonna have 2 products at least. It'll be very difficult to get my handle back. So once I have my handle, I'll be careful not to kill it. Okay? And you could have, you actually, what I was saying about, you could have gone sodium and ammonia at minus 30 degrees here. You could have, I'll put it in brackets. It's a difficult reaction, okay? And I would totally accept that if you put that in there. Practically, if we were working the project together in the lab, I'm gonna go try Lindlar. Setting that one up, like I said, is a little difficult. Yes?
So would you always use an ACN to put a carbon?
Yeah, except, okay, so if I would have given you, well, you wanna try another one? How much time do we have? You have 10 minutes, okay? Your turn. Okay, let's try it, because I'll show you. And the answer is, yeah, it depends on how many carbons you want. So if I were to give you, if I were to have given you this one, let's just keep it the same so that we see one and then do one. How would you synthesize this one? Okay, work on that. succinic acid is what it comes from. That's basically the lactam of succinate. So yeah, and yes, and specifically, my daughter's right, if it goes to the allylic or the benzoic without killing the handle. So that's the important part, the important part of MBS. Okay. Okay, so you're probably hunting around, how in the world did I put the nitrogen on there? And I only have 4 carbons, and I have 4 carbons. So I didn't put the nitrile on there, or I would have ended up with 5 carbons. So this then comes from the azo, okay, or the azide in this case. All right, so that's why those 2 reactions, they're in your last chapter. They're in the reduction chapter. They come from the bromide. Okay? So that's the new reaction. Up to this point, it follows that, right? So we're going to reduce anti-Markovnikov HBr peroxides, goes to here, right? So the only new reaction here is to go from here to here. I'm going to hit this with sodium azide. Again, that comes out of last semester where you have a good nucleophile here. Good nucleophiles do nice SN2 reactions, forming as a byproduct sodium bromide and putting that nitrogen on that carbon. Okay? That then, under hydrogen and palladium, will reduce to the amine. Okay? So again, this is kind of the practical working of the reactions that we're building in our toolbox. When we have a leaky faucet, we have to assess the tools that are needed to fix it and then fix it. Okay, that's what we're learning. Synthesis, when you look at the learning pyramid, there's 7 levels to the learning pyramid. Synthesis is level 6. It's difficult. You have to have base knowledge, how to apply it to a brand new novel situation. That's what very different use of knowledge than a lot of other courses, which again, that's why organic chemistry is different than a lot of other courses, which is why it's still the hallmark of, is this person a good memorizer, or are they a good thinker? Or the best, are they both? Okay? Because these are not easy. You have to memorize the base knowledge, now you have to apply it to you have to synthesize it in a brand new way. The 7th level, by the way, is assessment of your synthesis. This is assessment of what you're doing. Okay? And that's typically taught in grad school or above, right? Are we good? Workday Wednesday. We're gonna have a worksheet. I won't lecture. I'm gonna give you about half the day to go over it, and then half the day to correct it, and we'll do it together. Because I want you to know this. Did you guys get the email for lab tomorrow?
Yes.
I think our molecule actually shows up tomorrow afternoon, so that doesn't do us a lot of good. So we're going to do the Dilbala reaction, which is a super fun reaction. Okay, so we'll just keep your notebook. That's fine if we're switched from if you've already written up the normal lab or which of the oxidation lab. That's fine. Just move on to your next, and we'll come back to it. And we're still going to do the reaction, just not going to do it tomorrow.
Do you want the same notebook style that we did last
Yes.
time?
Yep.
Okay.
Follow exactly what Dr. Nagales had you guys build it.
Okay, same stuff?
Yep.
Okay.
Yep. Yep.
And
Okay.
then,
Yep.
I think in the syllabus it says if you type it up.
Oh,
Can we
I'm not.
type it up?
If you want to, I'm not. I'm not a sticker on that.
Okay, cool.
Yeah.